All right, so let's take a look now at some other examples of equations. We'll practice balancing these. So let's say we have nitrogen occurring as N2, reacting with hydrogen, H2, to produce ammonia, nitrogen trihydride, chemical name for it, NH3. Okay, so we're going to go through the same steps as we did previously. We're going to list the atoms that we have. So we have nitrogen, and we have H's on both sides, right? You have to have the same atoms on both sides, otherwise you've violated all sorts of laws already. So we're just going to count. Nitrogen on the left, we got 2. Nitrogen's on the right, we just have 1 there. H's on the left, we have 2. H's on the right, we have 3. So right now, nothing is balanced, right? So we need to balance them. And we're going to put our little lines in front to make sure that we're putting the coefficients in the right place. So what would we want to balance first? Well, since I listed nitrogen first, I can start with the nitrogen. You could also start with the H's. It doesn't really matter. You'll end up with the same answer. When it comes to balancing, practice does help because knowing what to start with first can actually get you to the answer a little bit quicker than other things that you start with. All right, so if I want to balance my nitrogens, well, nitrogens on the right side here are deficient, so we need to make more of them. So 1 times something needs to give me 2, so I'm going to put a 2. So 1 times 2 is 2n, but now I've also changed my hydrogens. So 2 times 3 is going to give me 6 H's. Well, now I need to make 6 H's on the left. 2 times what is 6? Well, 2 times 3 is 6, so I put a 3 in front. I didn't mess with the N2 over here, so that's still 1. Okay, this is your balanced equation for this particular reaction. Okay, let's take a look at another one. Let's say that I have, we'll do maybe propane. So propane has a formula C3H8, and it's going to react with oxygen, O2, to produce carbon dioxide, CO2, and then we're also going to get water, H2O. Okay, so that's my equation that represents this reaction of propane. This is what happens when you burn propane, for example. If a propane tank at home, this is what, if it burns completely, this is what you get. All right, I'm going to put my lines in front so I know where the coefficients are going to go. I'm going to list the atoms. So obviously I have carbon, I have H, and I have O. Okay, so I'm listing these and I'm going to count. On the left side, I have 3 C's. On the right side, I have just 1 C. On the left side, I have 8 H's. On the right side, I have 2 H's. On the left side, I have 2 O's. On the right side now, you can see the oxygen is split between the CO2 and the H2O. I have 2 O's here and another one. So 2 plus 1 gives me 3 oxygens. All right, so just upon initial inspection, nothing is balanced. And this brings us to the first sort of strategy that you can use when you balance your equation is if you notice that, or if you do notice that a particular atom or element is split between a couple different places, okay, what you can do is leave that one till the end to balance and balance the other ones first, because normally when you go through and you balance the other ones, that one ends up balancing itself, or it's just a one-step process. Now, you could by all means start with the O if you wanted to. It'll just take you a little bit longer. All right, so let's start with the C's. So I have 3 C's on the left. I want to make 3 C's on the right. Remember, subscript of 1 is understood. 1 times something should give me 3. So I'm going to put a 3 here. I've now changed my oxygens also, right? So 3 times 2 is the 6. Plus, don't forget there's an O over here as well. 6 plus 1 is 7. O's on the right. My C's are good. H's now. So I have 8 H's on the left. I need to make 8 H's on the right. So I have 2 originally. 2 times something give me 8. So that should be 4. So 4 times 2 is 8. But now I've also changed my oxygens. Right? So now I've made 4 times 1, 4 O's plus the 6 from over here. 6 plus 4 gives me 10. And this is the step that, especially when you first start balancing, that a lot of people forget to do, is the fact that, yes, I've changed my oxygens by putting this coefficient in front, but then don't forget you also have the oxygens over here in the CO2 as well. All right, so that's very easy to get tripped up with that. So make sure you're counting all the atoms. So we have 10 on the right side. I need to make 10 O's now on the left. So 2 times something gives me 10. So 2 times 5 is going to give me 10. All right, so my O's are good. H's we already balanced. C's are good. This then is your balanced equation for this particular reaction. Okay, and these are the smallest whole number ratios that you want. You could definitely balance it by, having a 2 and a 10 and a 6 and an 8, but you want to make sure that you get the lowest whole number ratios possible. All right, let's take a look at another one. Something very similar to this. And let's say now instead of propane, let's say that we have butane. So butane is going to have one extra carbon. So it's C4H10 reacting with oxygen, O2. And we're going to make the same products. We're going to get CO2, and then we're going to get H2O. Okay, so we're going to put our lines in front so we know where the coefficients are going to go. I'm going to list the atoms just like I did above. So we have C's, H's, and O's. And we're going to count these as well. So 4 C's here on the left side, 1 C on the right. I have 10 H's on the left. I have 2 H's here on the right side. I have 2 O's on the left. And then I have 2 here plus the 1. All right, so that gives me 3 O's on the right side. So again, going through the steps, I noticed the oxygen is split. I'm going to leave that till the end. Let's balance the carbons first. I need to make 1 times something gives me 4, so that's 4. 4 C's. I've changed my oxygens now. 4 times 2 is 8, plus that 1 is 9. Let's check out my H's. I have 10 H's on the left, so 2 times something should give me 10. 2 times 5. It's going to give me 10. I've changed my oxygens now, so 5 times 1 is 5, plus the 8 is going to give me 13. So now I need to make 13 O's on the left side. So 2 times something should give me 13. So you can do a quick math on that, right? So 2 times x is 13. What is x? Well, x would be 13 over 2, or 6.5, right? Should give you 13. And you can use that to help you balance the equation. So that's going to give me 13 here. Okay, so right now, technically, my equation is balanced. However, we want to make sure that we have whole numbers, right? So this is not a whole number. So the way that we convert it to a whole number is we just multiply it. What do we need to multiply it by to get the smallest whole number possible? Well, we're going to multiply it by 2 to get rid of the 2 on the bottom. And if I multiply this by 2, I need to multiply all the other coefficients by 2 as well. Okay, so when if I do that, I end up then, this was 1 here originally, so 1 times 2 is going to give me 2. 13 over 2 times 2 is going to give me 13 oxygens. 4 times 2 here is going to give me 8. And 5 times 2 is going to give me 10. Okay, so those are the smallest whole number ratios or whole number coefficients that you can possibly get. So 2, 13, 8, and 10. There's no whole number smaller than those. And we can double check now that our numbers are balanced. So if we look at our carbons now on the left side, so I have 2 times 4, so that's 8. On the right side, I have 8 times 1, so that's 8. Carbon's good. Hydrogens, 2 times 10 is 20. On the right side, 10 times 2 is 20. On the left side, I have 13 times 2, which is 26. And then on the right side, 8 times 2 is 16 plus 10, and that's 26 as well. All right, so that's your balanced equation for this reaction. So you will encounter situations like this, especially when it comes to reactions that look very similar to this. This is a very important type of a reaction that you're going to see lots of down the road. It's called combustion. When we look at reaction types, we will revisit this, but we need to make sure that we know how to balance these. All right, so that's one strategy that you can use, is to use a fraction or a decimal to help you balance the equation, and then get rid of the fraction at the end by converting it to a whole number. Whatever you multiply that coefficient by, all the other ones have to be multiplied by that same number as well. All right, let's take a look at the last example here, and this is going to be the other strategy that we can use to help balance an equation. So let's say I have the following. Let's say I have sodium hydroxide, so NaOH, reacting. Actually, let me change that. Let's do sodium carbonate, so Na2CO3, reacting with let's do calcium hydroxide, CaOH2, to produce calcium carbonate. And then I'm also going to get sodium hydroxide. Okay, so this looks a little bit more involved or complicated than the ones we saw previously, because there seem to be a lot more atoms involved, and it looks a little bit more complicated just in terms of the formulas. But we can simplify this so it's a lot easier to interpret. We're going to do the same thing. We're going to list the atoms that we have, but now, so we can see here we have our sodium on the left and the right. We have our calcium on the left and the right. And what you should hopefully also see that you have, yes, you have carbon, you have oxygen and hydrogen, but you should also notice that this CO3 here is one of those polyatomic ions that we talked about last time. And if you see the same polyatomic ion on the right side, then we can actually balance that as a group or as an entity. So you don't need to split it up into carbons and oxygens. I mean, you could, right? But it's going to take you a lot longer. If you notice that they're the same on both sides, balance them as a unit or as a group. Same thing with the OH, right? So our hydroxide is there on the left, and then we have the OH here on the right. You'll notice what I'm doing here is I'm putting the parentheses around the polyatomic ion, even if there isn't parentheses around them, so that I can, when I look at it, I can visually see it as it existing as a group. Okay, and then I can go ahead and balance. So, or make my inventories. I have two sodiums on the left. I have one sodium here on the right side. Calciums, I have one calcium here on the left. I have one calcium on the right. And now my carbonate. So I have one carbonate here. So look at outside the parentheses, one carbonate, and the carbonate is CO3. So one of it on the left, and I have one of it here on the right side. And then my hydroxides, I have two here on the left, and I have one here on the right side. Okay. This is going to be very helpful as you go through and balance your equations. It's going to, especially the ones that have polyatomic ions, it's going to make it way more efficient than trying to break it down into individual atoms. So now I can go ahead and balance. So I have two NAs on the left. I need to make two NAs on the right. So 1 times something is going to give me 2. So that obviously needs to be a 2. So this changes, whoops, that's the wrong thing. Changes my sodium to 2. But I've also changed my hydroxides now. So 1 times 2 is going to give me 2 hydroxides. Guess what? That automatically now balances my hydroxides. I balance the sodiums. We already have one calcium on either side, so the calciums are good. And I have one carbonate on either side as well. So this is your balanced equation. You only need just one of the, to change one of the coefficients in this case. All right, so again, make use of this as well when you balance your equations that do have polyatomic ions. So the strategy here is try to balance your polyatomic ions as groups, right? And that's if the ions are the same on the left side. for the reactant side and the product side. It's going to make it a lot quicker or a lot more efficient to do it that way.